Not just distant galaxies, not just the farthest stars, not even the entire observable universe. What if every telescope ever built, every spacecraft ever launched, every scientific discovery ever made has revealed only a small fragment of a reality so vast that our minds struggle to grasp it? Tonight, as you settle into the quiet and allow the noise of the day to drift away, I invite you to consider one of the most astonishing possibilities in modern cosmology. The universe may be far larger than anything we can ever see, and perhaps far larger than anything we can ever know. At first, that idea sounds strange. After all, when we look at images from powerful telescopes, the universe already appears immense beyond comprehension. We see countless galaxies scattered across the darkness, each containing billions or even trillions of stars. We see cosmic structures stretching across distances measured in millions of light years. Surely that is already everything. Surely there must be an edge somewhere, a boundary, a final wall, a place where the universe simply ends. Yet modern astronomy suggests something profoundly different. The limit of what we can observe is not necessarily the limit of what exists. In fact, those two things may be dramatically different. Imagine standing alone on a small boat in the middle of the ocean. The horizon surrounds you in every direction. To your eyes, it seems like the edge of the world. Beyond that horizon, nothing can be seen. But you know the ocean continues far beyond your view. The horizon is not a physical boundary. It is simply the limit of what you can observe from where you are. The observable universe works in a remarkably similar way. When astronomers speak about the observable universe, they are referring to the region of space whose light has had enough time to reach us since the beginning of cosmic expansion. Because light travels at a finite speed, we cannot instantly see every part of reality. We can only see as far as light has been able to travel during the age of the universe. Everything beyond that distance remains hidden, not because it does not exist, but because its light has not yet arrived. This distinction is one of the most important ideas in cosmology. The observable universe is not necessarily the whole universe. It is simply the portion available to observation. And that realization opens the door to an extraordinary possibility. The true universe could extend far beyond our cosmic horizon, perhaps thousands of times larger, perhaps millions, perhaps infinitely larger. No one knows. That uncertainty itself is part of the mystery. The observable universe spans roughly 93 billion light-years across. Even that number is difficult to comprehend. If you could travel at the speed of light, moving faster than anything with mass is allowed to move, crossing this visible region would still require tens of billions of years. Human civilization has existed for only a tiny fraction of that time. Recorded history barely registers against such scales. Yet astonishingly, this enormous cosmic sphere may represent only a small patch within a much larger reality. Imagine finding a single grain of sand on a vast beach. From that grain alone, you might learn something about the beach, its composition, its color, its texture, but you would not automatically know how large the beach truly is. In a similar way, humanity may be studying one tiny sample of a much grander cosmos. And if that is true, then countless galaxies may exist forever beyond our reach. Entire clusters of stars, immense cosmic structures, perhaps regions containing phenomena unlike anything we have ever observed, all permanently hidden behind the horizon of observable space. There is something both humbling and beautiful about this possibility. Throughout history, humans have repeatedly discovered that reality is larger than it first appears. Ancient civilizations once believed their lands were the center of the world. Later, people learned that Earth is a planet orbiting the sun. Then they discovered that the sun is merely one star among hundreds of billions within the Milky Way. Eventually, astronomers realized that the Milky Way itself is only one galaxy among countless others. Each discovery expanded the known universe. Each revelation moved humanity away from the center. And perhaps this journey is not over. Perhaps the observable universe is simply the next horizon, waiting to be surpassed conceptually. The deeper scientists investigate cosmic expansion, the more fascinating the picture becomes. Space itself is expanding. Galaxies are not simply flying through empty space. Rather, the fabric of space between distant galaxies is stretching. As this expansion continues, some regions of the universe become increasingly unreachable. Light emitted today from sufficiently distant locations may never reach Earth. The gap grows faster than the light can cross it. Those regions are not disappearing. They are simply becoming isolated from us forever. This creates a remarkable situation. There may be parts of the universe that exist right now, filled with stars and galaxies, yet no information from them will ever arrive here. No future telescope will reveal them. No future civilization will visit them. No signal will ever bridge the distance. They remain real, yet permanently beyond observation. And perhaps that is one of the most profound ideas science has ever uncovered. The universe may not be a complete picture waiting to be fully revealed. Instead, it may be a reality so vast that some portions are fundamentally inaccessible. Not hidden by technology, not hidden by lack of knowledge, but hidden by the very structure of space and time itself. As we continue this journey tonight, keep that possibility gently in mind. The stars above may already seem endless. The galaxies may already feel impossibly distant. And yet, beyond everything we can see, there may be an even greater cosmos waiting in silence, a universe beyond the universe we know. For decades, this mystery quietly haunted cosmology. The numbers seem straightforward. When astronomers studied the early universe through the faint glow of the cosmic microwave background and examined the abundance of hydrogen and helium created shortly after the Big Bang, the calculations repeatedly pointed toward the same conclusion. A certain amount of ordinary matter should exist. Not dark matter, not dark energy, just normal matter. The kind made of protons, neutrons, and electrons. The kind that forms stars, planets, oceans, mountains, trees, and every living creature that has ever existed. And yet, when astronomers searched the modern universe and added everything together, something didn't make sense. Galaxies contained enormous quantities of stars. Clusters of galaxies contained vast clouds of hot gas. Nebulae drifted between stars. Dust floated through space. But even after counting all of it, a surprisingly large fraction of the universe's ordinary matter seemed to be missing. It was as if someone had removed huge portions of the cosmic inventory and hidden them somewhere beyond detection. The mystery became even more intriguing because astronomers were not talking about dark matter. Dark matter is already invisible by definition. Scientists know it exists because of its gravitational influence. The missing matter mystery was different. This missing material was supposed to be ordinary matter. The same type of matter that makes up you, the same type of matter that makes up Earth, the same type of matter that forms every star shining in the night sky. If it existed, it should have been detectable somehow. Yet for years, nobody could find it. Imagine performing an inventory of an enormous library. You count every shelf, you count every book, you double-check every room. Then you discover that nearly half the books listed in the catalog are nowhere to be found. You know they must exist because the records prove they were there. But no matter how carefully you search, they remain absent. That was essentially the challenge facing cosmologists. The universe's accounting books insisted that the matter existed. Observations seemed to disagree. And whenever nature presents a discrepancy like that, scientists become fascinated because discrepancies often lead to discoveries. Sometimes the measurements are wrong. Sometimes the theories are incomplete. And occasionally the universe reveals something entirely unexpected. As researchers searched for answers, they began looking beyond the obvious places. Perhaps the missing matter was not concentrated inside galaxies. Perhaps it was not shining brightly enough to attract attention. Perhaps it was spread so thinly across space that it had become nearly invisible. That possibility led astronomers toward one of the most remarkable ideas in modern cosmology. What if the missing matter was hiding between galaxies? When most people picture the universe, they imagine galaxies floating through empty space. But space between galaxies is not completely empty. Far from it. Even the enormous voids separating cosmic structures contain particles, magnetic fields, and diffuse gas. The challenge is that this material can be extraordinarily thin. A region of intergalactic space may contain only a few particles per cubic meter. Compared to Earth's atmosphere, that is almost unimaginably sparse. Detecting such material is incredibly difficult. It does not glow brightly. It does not form stars. It does not create obvious structures visible through ordinary telescopes. Yet when stretched across millions of light years, even extremely diffuse matter can add up to an enormous amount of mass. Slowly, evidence began to accumulate. Computer simulations suggested that galaxies were not isolated islands. Instead, they appeared connected by enormous filaments of gas and dark matter, forming what scientists call the cosmic web. Across these gigantic structures, matter flowed like rivers feeding growing cities. Galaxies formed where filaments intersected. Clusters emerged at the densest junctions, and between them stretched vast networks of nearly invisible material. The missing matter might not have been missing at all. It might simply have been hiding in the largest structures the universe ever created. This realization transformed the search. Astronomers began developing increasingly sophisticated techniques. Instead of looking directly for glowing objects, they searched for subtle fingerprints. When light from distant quasars passed through diffuse intergalactic gas, tiny portions of that light were absorbed. These absorption signatures acted like invisible barcodes. By studying them carefully, scientists could detect material that otherwise remained unseen. The process required patience. The signals were faint. The measurements were delicate. Years of observations had to be combined and analyzed, yet gradually a picture began to emerge. The missing matter seemed to exist within enormous reservoirs of warm, hot gas stretching between galaxies, not cold enough to form stars, not hot enough to glow brightly in visible light, occupying a difficult middle ground that made detection extraordinarily challenging. This material became known as the warm, hot intergalactic medium, often abbreviated as WHIM. Despite the playful acronym, the discovery represented a major achievement. For decades, cosmologists had been searching for missing pieces of the universe. Now, they were finally beginning to find them. What makes this story especially beautiful is how it changes our perspective on emptiness. Regions that appear vacant are often anything but empty. The darkness between galaxies is not simply blank space. It is part of a vast cosmic ecosystem. Matter moves through it. Energy flows across it. Galaxies exchange material with it. Over billions of years, this diffuse medium helps shape the evolution of the entire universe. In a sense, the missing matter mystery reminds us that some of nature's most important structures are also its hardest to see. The brightest objects naturally capture our attention. Stars dazzle, galaxies inspire, nebulae glow with spectacular colors. But sometimes the greatest discoveries are hidden within things that barely shine at all. The universe often keeps its secrets in quiet places, and perhaps that is one reason this mystery remains so captivating. It reveals that even after centuries of astronomical exploration, the cosmos still contains hidden chapters waiting to be uncovered. Not hidden beyond our reach, not hidden through impossibility, but hidden because nature is more subtle than our first assumptions. The missing matter was never truly gone. It was woven into the vast architecture of the cosmic web, spread across unimaginable distances, patiently waiting for humanity to develop the tools needed to find it. And in discovering where it was hiding, astronomers gained something even more valuable than a solution. They gained a deeper understanding of how the universe itself is connected. The galaxies we admire are only part of the story. Between them lies an immense and delicate network of matter stretching across the cosmos like invisible threads. And those threads may be just as important as the galaxies they connect. The missing matter mystery eventually led astronomers toward hidden reservoirs of gas woven throughout the cosmic web. The matter was difficult to find, but it was still matter. It followed familiar rules. It belonged to the world of known physics. Dark energy is different. It is not simply something we have misplaced. It is something we do not understand at all. And yet it may be the single most important ingredient shaping the future of the entire universe. Imagine standing on a vast shore and watching distant boats drift away across the ocean. At first, that movement would seem perfectly natural. Perhaps a current is carrying them. Perhaps the wind is pushing them. Now imagine noticing something strange. The boats are not merely moving apart. They are accelerating. The farther away they get, the faster they recede. And no matter how carefully you search, you cannot identify what force is driving the acceleration. That is remarkably similar to what astronomers discovered on a cosmic scale. For much of the 20th century, scientists assumed that the expansion of the universe should be slowing down. After all, gravity pulls matter together. Every galaxy exerts gravitational attraction on every other galaxy. The universe contains immense amounts of mass. Stars, planets, gas clouds, black holes, and dark matter all contribute to the cosmic gravitational field. Logic suggested that gravity should gradually act as a brake. The expansion that began with the Big Bang should continue, but more slowly over time. It seemed reasonable, elegant even. Then the universe surprised everyone. In the late 1990s, two independent teams of astronomers were studying distant exploding stars known as Type 1a supernovae. These stellar explosions are extraordinarily useful because they shine with predictable brightness. By comparing how bright they appear from Earth to how bright they truly are, astronomers can estimate their distances. The researchers hoped to measure how the expansion of the universe had changed over billions of years. The results were expected to reveal a slowing cosmos. Instead, they found the opposite. The distant supernovae appeared dimmer than expected. The only explanation that fit the observations was astonishing. The universe was not slowing down. It was speeding up. The expansion itself was accelerating. The discovery was so unexpected that many scientists initially questioned the data. Surely there must be an error. Perhaps dust was interfering with the measurements. Perhaps the supernovae behaved differently in the distant past. Perhaps some overlooked factor was creating an illusion. Yet as more observations accumulated, the conclusion became increasingly difficult to escape. The acceleration was real. Something was pushing the universe apart, and nobody knew what it was. This mysterious influence eventually became known as dark energy. The name sounds dramatic, almost poetic, but in truth, it reflects uncertainty more than understanding. The word dark does not mean evil or sinister. It simply means hidden, unknown, unexplained. Dark energy is a label for a phenomenon that scientists can observe but cannot fully describe. In some ways, it is a placeholder for ignorance, a name attached to one of the greatest unanswered questions in modern physics. What makes dark energy especially strange is that it appears to dominate the universe. Ordinary matter, the stars, planets, galaxies, and everything visible, accounts for only a small fraction of cosmic reality. Dark matter contributes much more. But dark energy appears to make up nearly 70% of the total energy content of the cosmos. Think about that for a moment. The vast galaxies we admire through telescopes, the brilliant stars lighting distant worlds, the enormous clusters containing thousands of galaxies. All of that represents only a minor component of the universe. Most of reality appears to consist of something we do not understand. That realization has a wonderfully humbling quality. Humanity often feels advanced. We have mapped genomes, built spacecraft, split atoms, walked on the moon. Yet when we examine the universe as a whole, we discover that most of it remains mysterious. Dark energy serves as a reminder that our understanding is still incomplete. The deeper we look, the more questions emerge. One possibility is that dark energy represents a property of empty space itself. That idea sounds simple at first, but it quickly becomes astonishing. Empty space is often imagined as nothingness, a blank stage upon which cosmic events unfold. Modern physics paints a different picture. Even the emptiest regions of space are not truly empty. Quantum fields permeate the vacuum. Tiny fluctuations occur constantly. Energy may exist even where no particles are present. If space itself contains an intrinsic energy, then as the universe expands and creates more space, it also creates more of that vacuum energy. The result could be a persistent outward pressure, a gentle but relentless force driving cosmic acceleration. This concept traces back to ideas first explored by the physicist Albert Einstein. Ironically, Einstein once introduced a mathematical term known as the cosmological constant to keep the universe static. When evidence later showed that the universe was expanding, he reportedly regretted the addition. Yet decades later, the cosmological constant returned in a completely unexpected way. It became one of the leading candidates for explaining dark energy. The universe, it seems, has a talent for revisiting old ideas, and sometimes those ideas become important for reasons nobody originally imagined. The consequences of dark energy extend far beyond academic curiosity. They shape the destiny of everything that exists. If dark energy continues behaving as it does today, galaxies will drift farther and farther apart. Over immense spans of time, distant galaxies will disappear beyond the cosmic horizon. Future observers living trillions of years from now may see a dramatically different sky. Many of the galaxies visible today will have vanished from view, not because they ceased to exist, but because expanding space carried them beyond the reach of light. The cosmos could become increasingly lonely. Future civilizations might look outward and see only their local galactic neighborhood surrounded by darkness. The evidence for the Big Bang itself could become difficult to detect. The rich cosmic landscape visible today might eventually fade from sight. There is something haunting about that possibility. The universe may currently exist during a particularly fortunate era, an age when enough cosmic history remains visible for intelligent observers to reconstruct the story of expansion. A window of opportunity. A brief chapter in an unimaginably long cosmic timeline. Dark energy reminds us that the universe is not static. It is dynamic, evolving, changing in ways that unfold across billions and trillions of years. And perhaps the most remarkable aspect of all is that we still do not know the full answer. The force accelerating the cosmos remains hidden behind layers of mystery. Astronomers can measure its effects. Physicists can build models. Observatories can gather increasingly precise data. Yet the true nature of dark energy continues to evade complete understanding. The universe is expanding faster and faster. We know that much. But why? That question remains open. And somewhere beyond the galaxies, beyond the cosmic web, beyond the furthest light that reaches our telescopes, the answer may already be woven into the fabric of reality itself. If you're enjoying tonight's quiet journey through the unknown universe, consider subscribing and joining us for more relaxing explorations beneath the stars. Because the deeper we travel into the cosmos, the more extraordinary its mysteries become. There is something uniquely unsettling about the word before. In everyday life, every event has a cause. Every beginning seems connected to something that came earlier. A sunrise follows a night. A tree grows from a seed. A river begins from melting snow or underground springs. Our minds are built to think this way. Whenever we encounter a beginning, we instinctively ask what came before it. And so, when we learn that the universe itself appears to have begun nearly 13.8 billion years ago, in an event we call the Big Bang, the question feels unavoidable. What happened before? What existed before space expanded? What existed before time began flowing? What existed before everything? The difficulty is that modern physics offers an answer that sounds almost impossible to accept. It may be that the question itself does not work in the way we imagine. According to our best current understanding, the Big Bang was not an explosion occurring inside an already existing universe. Instead, it marked the earliest moment at which space and time themselves can be meaningfully described. That means time may not have existed in any recognizable form before the Big Bang. And if there was no time, then asking what happened before becomes strangely complicated. It is a little like asking what lies north of the North Pole. The question sounds sensible at first, yet the closer you examine it, the more you realize that the concept itself may break down. The North Pole is the northernmost point. There is no farther north. Likewise, the Big Bang may represent a boundary beyond which the familiar concept of time no longer applies. This idea is profoundly difficult for human intuition. We live inside time. Every memory we have is arranged within it. Every experience depends upon it. To imagine existence without time is like trying to imagine a color that has never existed, or a sound beyond all possible hearing. The mind reaches for something familiar and finds nothing to hold on to. Yet this possibility remains one of the most serious scientific answers currently available. The beginning of time itself may have occurred alongside the beginning of the observable universe. But science is rarely satisfied with a single possibility. And because the earliest moments of cosmic history remain hidden behind extreme conditions, many alternative ideas continue to be explored. Some researchers wonder whether our universe emerged from a previous universe. In this picture, the cosmos did not begin from absolute nothingness. Instead, it may have inherited its existence from something older. One fascinating proposal suggests that the universe undergoes endless cycles. Expansion is followed by contraction. A cosmic ending eventually becomes a new beginning. a universe collapses. Then another is born, again and again, across unimaginable spans of time. If such cycles occur, then the Big Bang might not have been the first beginning at all. It may simply have been the latest chapter in an infinitely repeating story. There is something strangely comforting about this possibility. Instead of a single creation event emerging from mystery, existence becomes an eternal rhythm. Birth, growth, decline, renewal. A cosmic heartbeat stretching across eternity. Whether nature actually works this way remains unknown, but the idea continues to inspire both scientists and dreamers. Other theories imagine an even stranger possibility. Perhaps our universe is only one member of a vast collection of universes, a multiverse. In some versions of this concept, space continuously produces new universes, like bubbles forming within an endlessly expanding cosmic ocean. Each bubble becomes its own universe. Each develops its own history, its own stars, its own galaxies, its own future. If this is true, then the Big Bang may not have been the beginning of everything. It may have been only the birth of our particular cosmic region. Beyond the limits of what we can observe, countless other universes could potentially exist. Most would remain forever inaccessible. No spacecraft could reach them. No telescope could photograph them. They would exist beyond the horizons imposed by space itself. The thought is breathtaking. Everything humanity has ever seen might represent only one tiny fragment within a much larger reality. Yet there is an important challenge. Scientific ideas must ultimately connect to evidence. And evidence becomes difficult when dealing with regions that may forever remain beyond observation. That is why the multiverse remains one of the most controversial concepts in modern cosmology.
It is fascinating. It is mathematically motivated in some theories, but it is also extraordinarily difficult to test directly, and science advances most confidently when observations guide the way. Then there is perhaps the most mysterious possibility of all. Maybe the universe emerged from the quantum world. At the smallest scales known to physics, reality behaves in ways that seem deeply unfamiliar. Particles appear and disappear. Probabilities replace certainty. Empty space is not truly empty. Instead, it seethes with tiny fluctuations and restless activity. Some physicists have proposed that the universe itself could have originated from a quantum process, not from ordinary nothingness, but from a state so fundamentally different from everyday experience that our language struggles to describe it. This idea often creates confusion because the word nothing carries many meanings. In ordinary conversation, nothing means complete absence. No matter, no energy, no space, no time. But in physics, the concept becomes more subtle. What appears empty may still contain structure, fields, potential, possibilities. The distinction matters enormously, and it reveals how challenging these questions truly are. Even our words become uncertain at the edge of understanding. Perhaps that uncertainty is exactly what makes this subject so captivating. The deeper we investigate cosmic origins, the more we discover that reality may be stranger than common sense allows. Questions that seem simple become difficult. Definitions begin to blur. The familiar foundations of space, time, cause, and effect start to wobble. And yet, this is not a sign of failure. It is a sign that we have reached one of the genuine frontiers of knowledge. The history of science is filled with moments when familiar intuition had to be abandoned. The Earth was not the center of the cosmos. Time was not absolute. Space could bend. Light behaved both like a wave and a particle. Each discovery initially felt impossible. Each forced humanity to expand its understanding. The mystery of what happened before the Big Bang may eventually require a similar transformation. The final answer, if one exists, could be something no human civilization has yet imagined. That possibility is both humbling and beautiful, because it reminds us that the universe is not obligated to fit comfortably inside our expectations. There may come a day when future astronomers possess instruments far beyond anything we can currently build. They may detect subtle clues hidden in ancient radiation. They may uncover evidence of previous cosmic cycles. They may find signatures suggesting the existence of other universes. Or they may discover an explanation entirely different from every theory proposed today. For now, however, the mystery remains open. And perhaps that openness is part of its power. When we look into the night sky, we often think about distance. the billions of stars, the vast galaxies, the enormous stretches of space. Yet some of the deepest mysteries are not far away at all. They lie at the very beginning, at the first moment, at the boundary where knowledge fades into speculation. The Big Bang explains an extraordinary amount about the evolution of the cosmos, but the question of what came before continues to linger quietly at the edge of science, waiting, inviting curiosity, reminding us that even after centuries of discovery, the universe still holds secrets vast enough to challenge the imagination itself. And somewhere beyond that first known moment, hidden behind the veil of cosmic origins, lies one of the greatest unanswered questions humanity has ever asked. There is something strangely unsettling about the oldest light in the universe. Not because it is violent, not because it is dangerous, but because it is supposed to be predictable. The cosmic microwave background, the faint afterglow left behind by the Big Bang, has been studied for decades. It surrounds us in every direction, filling the universe with a nearly uniform sea of ancient radiation that has traveled across space for more than 13 billion years. When astronomers first mapped this relic light in detail, they expected to find tiny variations, small differences in temperature, tiny fluctuations that would eventually become galaxies, stars, planets, and everything we know today. And that is exactly what they found. Almost. Because hidden within that ancient light was something unexpected, something unusually large, something unusually cold. A region so enormous that it immediately raised questions. A place now known simply as the cold spot. And even today, no one can say with complete certainty why it exists. The cold spot appears as a giant patch in the cosmic microwave background that is slightly cooler than the surrounding regions. The temperature difference is tiny, only a fraction of a degree above absolute zero. Yet on cosmic scales, the anomaly is enormous. It spans a region of the sky so vast that it covers an area many times larger than the full moon appears from Earth. At first glance, this might not sound particularly dramatic. After all, the early universe was not perfectly smooth. Tiny fluctuations existed everywhere. Some regions were slightly hotter, some slightly colder. Those variations are expected. They are part of the reason galaxies eventually formed. But the cold spot appears larger and more pronounced than many standard cosmological models predict. And that is where the mystery begins. Imagine throwing a handful of pebbles into a perfectly calm pond. You expect ripples, you expect patterns, but then you notice one unusually large wave appearing far from where it should be. Maybe it happened naturally. Maybe it is simply a rare coincidence. Or maybe something else caused it. The cold spot occupies a similar place in modern cosmology. It might be nothing more than an extraordinarily unlikely fluctuation, yet its existence continues to invite alternative explanations, and some of those explanations are fascinating. One possibility involves something called a supervoid. A supervoid is exactly what it sounds like, a gigantic region of space containing far fewer galaxies than average. The universe is not evenly filled with matter. Instead, galaxies gather into enormous filaments and clusters, leaving vast, empty regions between them. Some of these voids are astonishingly large. If a particularly massive supervoid happened to sit between Earth and the cold spot, it could influence the light traveling through it. As ancient photons from the cosmic microwave background pass through the void, they interact with the changing geometry of space-time. Because the universe is expanding, the photons may lose a tiny amount of energy during their journey. That energy loss would make them appear slightly colder when they finally reach us. For years, astronomers searched for evidence of such a structure. Several observations suggested that a large, underdense region might indeed exist in roughly the same direction. Yet the puzzle remains unresolved. The observed void may not be large enough to fully explain the cold spot. It helps, but it does not completely solve the mystery. And so the debate continues. Could the cold spot simply be a statistical accident? This explanation may sound disappointing at first, yet science often teaches us that rare events happen naturally. If the universe contains enough fluctuations, eventually one of them will be unusually extreme. Imagine rolling dice millions of times. Most results appear ordinary, but occasionally an unlikely sequence emerges. Not because new physics is involved, not because the rules have changed, but simply because probability allows rare outcomes. Some cosmologists argue that the cold spot may be exactly this kind of event, an unusually large fluctuation that stands out because human beings are naturally drawn toward anomalies. After all, if no strange regions existed anywhere in the sky, that might be even more surprising. Yet many researchers remain intrigued because the cold spot feels just unusual enough to keep the conversation alive. And whenever an anomaly survives decades of scrutiny, curiosity naturally follows. Some of the most imaginative explanations venture even further. A few theoretical proposals suggest that the cold spot could be evidence of exotic phenomena from the earliest moments of cosmic history. Perhaps it reflects unusual conditions during cosmic inflation. Perhaps it preserves traces of structures that existed when the universe was unimaginably young. Some have even speculated about collisions between our universe and another universe during the inflationary era. This idea sounds like science fiction, and it is important to emphasize that there is currently no convincing evidence supporting such a scenario. Yet the fact that scientists can seriously explore these possibilities reveals something beautiful about astronomy. When observations refuse to fit neatly into expectations, they create opportunities for entirely new questions. Most extraordinary claims eventually turn out to have ordinary explanations, but every now and then, a genuine surprise emerges. The challenge is learning which anomalies deserve patience and which simply reflect chance. The cold spot sits precisely at that fascinating boundary. It is strange enough to inspire bold ideas, yet not strange enough to overturn established cosmology, at least not yet. One reason the cold spot continues to captivate astronomers is that it reminds us how incomplete our understanding can be. The standard model of cosmology has been remarkably successful. It explains the expansion of the universe, the formation of galaxies, the distribution of large-scale structure, the patterns observed in the cosmic microwave background. Again and again, its predictions have matched observations with astonishing precision. Yet even highly successful models leave room for mysteries, and sometimes those mysteries become the most valuable clues. History shows that scientific progress often begins with small discrepancies, a tiny inconsistency, a curious observation, a detail that refuses to disappear. The cold spot may ultimately prove entirely ordinary. Future data may show that it is simply an improbable fluctuation amplified by human attention. But even if that happens, the investigation itself has value, because every attempt to understand the anomaly teaches us more about the universe. Astronomers have refined their measurements, improved their models, mapped enormous structures across billions of light years, and explored possibilities that might otherwise never have been considered. In that sense, the cold spot has already succeeded. It has forced us to look deeper, and perhaps that is one of the most important roles a mystery can play. The universe often appears orderly when viewed from a distance. Galaxies follow gravity. Stars evolve according to well-understood physics. Cosmic structures emerge from patterns that scientists can model with remarkable accuracy. Yet every so often, something unexpected appears. A small irregularity, a subtle deviation, a patch of ancient light that seems just a little colder than it should be. And suddenly, the cosmos feels mysterious again. The cold spot reminds us that even after centuries of observation, the universe still contains questions waiting patiently in the dark. Questions that may have simple answers. Questions that may reveal something deeper. Questions that encourage us to keep looking. Because sometimes the most interesting discoveries are not the things we understand. They are the things that quietly refuse to be explained. And somewhere within the oldest light in existence, one of those questions still lingers. A cold shadow, a faint anomaly, a tiny temperature difference stretched across unimaginable distances, waiting for the day when its story is finally understood. The idea sounds almost impossible at first. Everything we can see, the galaxies, stars, planets, black holes, nebulae, and even the faint glow left behind by the Big Bang, might be only a tiny portion of a far greater reality. And if that possibility is true, then one of the most profound questions in cosmology emerges. What if our observable universe is not the entire universe at all? What if it is merely one bubble floating inside something vastly larger? Tonight, we drift gently into one of the strangest ideas modern physics has ever considered. The possibility that our entire observable cosmos could be only a small region inside an enormous cosmic bubble.
And perhaps beyond it, there may be countless others. The concept begins with a simple fact that often surprises people. When astronomers talk about the observable universe, they are not talking about the entire universe. They are talking only about the portion whose light has had enough time to reach us since the beginning of cosmic expansion. The universe is approximately 13.8 billion years old. But because space itself has been expanding during that time, the observable universe stretches much farther than 13.8 billion light-years. Today, the radius of the observable universe is estimated to be about 46 billion light-years in every direction. That sounds unimaginably large, and it is. Yet the key word remains observable. Everything beyond that boundary remains hidden from view. Not because telescopes are too weak, not because the light is faint, but because the light has simply not had enough time to arrive. There may be more universe beyond that horizon, much more, perhaps infinitely more. This realization changes the way we think about cosmic geography. The observable universe is not necessarily the edge of existence. It is simply the edge of what we can currently see, like standing on a beach and seeing only as far as the horizon. The ocean does not end where your vision stops. Your vision simply stops there. Many cosmologists believe the same may be true of the universe itself. The visible region may be only a small patch inside a much larger cosmic expanse. And that possibility naturally raises another question. If the universe extends far beyond our horizon, could different regions be fundamentally different from our own? This idea gained attention through a theory known as cosmic inflation. Inflation proposes that in the earliest fraction of a second after the Big Bang, the universe expanded at an astonishing rate, far faster than the speed of light itself. Not because matter traveled through space that quickly, but because space itself stretched. A tiny microscopic region suddenly became enormous. Inflation helps explain several mysteries. It explains why the universe appears remarkably uniform on large scales. It explains why distant regions have similar temperatures, and it explains why space appears nearly flat. But inflation may have led to something even stranger. Some versions of inflation suggest that the process never completely ended. Instead, certain regions stopped inflating and formed universes like ours. Meanwhile, other regions continued expanding, and continued, and continued, like bubbles forming inside an endlessly growing cosmic foam. This concept is sometimes called eternal inflation. According to this picture, our observable universe could be one bubble among countless others. Each bubble may contain its own stars, its own galaxies, perhaps even its own laws of physics. The image is both beautiful and unsettling. Imagine standing inside a single bubble, floating in an endless cosmic sea. Everything humanity has ever known exists inside that one bubble. And beyond its invisible walls may lie realms forever unreachable. The fascinating part is that this idea did not emerge from science fiction. It emerged from attempts to solve real mathematical problems in cosmology. The equations themselves opened the door, and once that door opened, researchers discovered that the implications were enormous. Some bubble universes might resemble our own. Others could be dramatically different. Perhaps gravity behaves differently there. Perhaps atoms cannot form. Perhaps stars never ignite, or perhaps entirely unfamiliar structures emerge. The possibilities become difficult to imagine because our minds evolved inside only one version of reality. We naturally assume that the laws of nature we observe are universal. But what if they are merely local? What if our bubble happens to possess a specific set of physical properties among many possibilities? This question touches one of the deepest mysteries in physics. Why do the constants of nature have the values they do? Why is gravity as strong as it is? Why does dark energy have the value we measure? Why do elementary particles possess their particular masses? Small changes to these numbers could produce a radically different universe. Stars might never form, galaxies might never emerge, life might never become possible. Some physicists wonder whether our universe appears finely tuned because many cosmic bubbles exist. If enough universes are produced, eventually some will possess the conditions necessary for complexity.
and naturally, observers would arise only within those hospitable regions. It is a controversial idea. Not everyone agrees with it, yet it remains one of the most intriguing possibilities in modern cosmology.
The challenge is that testing such ideas is extraordinarily difficult. If other bubbles exist beyond our observable horizon, how could we ever detect them? At first glance, it seems impossible. Anything outside our cosmic horizon appears permanently hidden, but some scientists have proposed subtle clues. If two expanding bubble universes collided long ago, they might have left faint signatures in the cosmic microwave background. That ancient light still fills the universe today. Tiny patterns within it could potentially reveal evidence of encounters between neighboring bubbles. Researchers have searched for such signs. So far, no definitive evidence has emerged. The data remain inconclusive. The mystery remains open. And perhaps that uncertainty is part of what makes the idea so captivating. We are exploring questions at the limits of observation itself, questions where imagination and mathematics travel farther than telescopes currently can. There is something deeply humbling about this possibility. For centuries, humanity repeatedly discovered that our position in the cosmos was not as central as once believed. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The Milky Way was not the center of the universe. And perhaps someday we may learn that our observable universe is not the whole cosmos either, merely one region among many, one bubble among countless bubbles, one chapter inside a story vastly larger than we can currently read. Whether that vision ultimately proves correct remains unknown. Science has not yet reached a final answer. But the possibility itself invites a remarkable perspective. The stars above us already seem infinite. The galaxies already stretch beyond ordinary comprehension. Yet the universe may still be hiding scales of reality, far beyond even those immense distances. And somewhere beyond the cosmic horizon we can never cross, reality may continue unfolding in ways we have not yet imagined. The universe may be larger than we can see. The cosmos may be stranger than we can measure. And perhaps our tiny corner of existence is only one small bubble floating quietly within an ocean without end. The cosmic web is one of the most astonishing discoveries in modern astronomy because it reveals that the universe is not a random scattering of galaxies drifting aimlessly through darkness. Instead, on the largest scales ever observed, galaxies appear arranged along enormous filaments that stretch across hundreds of millions of light years, connecting clusters, groups, and superclusters into a vast network that spans the observable cosmos. For much of human history, the night sky looked like a collection of isolated points of light. Even after telescopes revealed countless galaxies beyond the Milky Way, many people imagined them as separate islands floating independently through space. But as astronomical surveys became more powerful, a different picture slowly emerged. The universe seemed to possess structure, and not just structure on the scale of galaxies, not just structure on the scale of galaxy clusters, but structure on scales so immense that the mind struggles to hold them all at once. Imagine flying far beyond our Milky Way, past neighboring galaxies, past giant clusters containing thousands of galaxies, past enormous superclusters stretching across unimaginable distances. As your view expands, something unexpected begins to appear. The galaxies are not distributed evenly. Instead, they gather into long strands. These strands intersect like threads woven into an enormous cosmic tapestry. Between them lie vast empty regions, known as cosmic voids. Some of these voids are so enormous that millions of galaxies could fit inside them, yet they remain surprisingly empty. The result resembles something between a spider web, a network of rivers, and the branching patterns found inside living organisms. This structure is what astronomers call the cosmic web, and it may be the largest known pattern in the entire universe. What makes this discovery even more remarkable is that much of the web is invisible. The glowing galaxies we observe are only the bright markers tracing a much larger framework. Beneath them lies something hidden, something that outweighs ordinary matter many times over: dark matter. Although dark matter cannot be seen directly, its gravitational influence appears to shape the architecture of the cosmos. In the early universe, tiny fluctuations in density were present within the hot sea of matter and radiation.
These fluctuations were incredibly small, yet gravity amplified them over billions of years. Regions that contained slightly more matter attracted additional material. As more matter accumulated, those regions became even stronger gravitational wells. Slowly, immense dark matter structures began to emerge. Ordinary matter followed. Gas flowed toward these invisible concentrations. Stars formed. Galaxies appeared. Clusters assembled. And gradually, the cosmic web took shape. In many ways, dark matter may have acted like the scaffolding of the universe. The luminous galaxies we admire today could simply be the visible decorations hanging upon an unseen framework. This idea is both elegant and unsettling. The grandest structure humanity has ever discovered may be largely composed of something we still do not fully understand. Astronomers have spent decades trying to map this hidden network. The task is extraordinarily difficult because the filaments themselves are often faint. Much of the material stretching between galaxies consists of thin gas spread across enormous distances. For years, scientists suspected these filaments existed primarily because computer simulations predicted them. Then, observations gradually began to reveal evidence supporting those predictions. Large galaxy surveys showed that galaxies naturally align along filamentary structures. Gravitational lensing measurements hinted at dark matter concentrations linking clusters together. Sensitive telescopes detected traces of hot gas stretched between massive cosmic structures. Piece by piece, the web emerged from theory into observation. What is fascinating is how closely the real universe resembles the simulations. Researchers can start with conditions measured shortly after the Big Bang and allow gravity to evolve those conditions over billions of years inside powerful computers. Again and again, the result looks remarkably similar to the observed cosmic web. Long filaments appear, dense knots form where filaments intersect, huge voids open between them. The resemblance is one of the great successes of modern cosmology. It suggests that the basic laws governing cosmic evolution are understood surprisingly well. Yet many mysteries remain. One of the strangest features of the cosmic web is the existence of the voids themselves. At first glance, empty space may seem uninteresting, but cosmic voids are among the largest structures in existence. Some stretch hundreds of millions of light years across. Inside them, galaxies are scarce, matter is thinly distributed, the darkness feels almost absolute. If you could somehow travel into the center of one of these giant voids, the night sky would look profoundly different. Neighboring galaxies would be fewer. The familiar richness of the cosmic landscape would fade. You would inhabit one of the loneliest places imaginable. And yet, these empty regions are just as important as the filaments. The web exists because matter gathers in some places and leaves others behind. The voids help define the structure just as much as the filaments themselves. Without emptiness, the pattern would not exist. The cosmic web also changes how we think about galaxies. Galaxies are not isolated objects. They are participants in a much larger story. Their growth often depends on where they reside within the web. Gas can flow along filaments, feeding galaxies and helping them form new stars. Clusters emerge where multiple filaments intersect. Galaxies collide more frequently in these crowded environments. Black holes grow. Star formation accelerates. Entire histories may be shaped by a galaxy's location within this enormous network. In a sense, every galaxy carries the influence of the web that surrounds it. Even our own galaxy is part of this grand structure. The Milky Way resides within a network of neighboring galaxies, connected through larger cosmic patterns. The night sky may feel local and familiar, but our home is embedded within structures stretching across distances almost impossible to comprehend. And perhaps the most beautiful aspect of the cosmic web is its unexpected familiarity. Nature often repeats certain patterns. River systems branch across continents. Lightning forks through the atmosphere. Neural networks spread throughout the brain. Tree roots explore the soil. The cosmic web seems to echo those same forms on a scale billions of times larger. The similarity does not mean these systems are identical. They arise through very different processes. Yet the visual resemblance reminds us that complexity can emerge from surprisingly simple rules. Gravity, acting patiently over billions of years, has woven a structure so vast that it connects galaxies across the observable universe. What began as tiny fluctuations shortly after the Big Bang eventually became the largest architecture known to science. And tonight, as we quietly contemplate that immense network stretching through the darkness, it becomes easier to appreciate how connected everything truly is.
The galaxies are not scattered randomly. They are threads in a cosmic tapestry. The clusters are knots in an ancient design. The voids are silent spaces between the strands. And the web itself continues stretching outward beyond every horizon we can see, connecting distant islands of light across a universe still far larger and more mysterious than we fully understand. If this cosmic web is stretching your imagination tonight, leave a comment sharing which mystery fascinates you most. Imagine drifting through the silent darkness between the stars. No sunrise, no sunset, no familiar sky. No bright star hanging overhead to mark the passing of time, only endless night. At first, that sounds impossible. We are so accustomed to thinking of planets as companions of stars that the very word planet almost seems incomplete without a sun nearby. Earth has the sun, Mars has the sun, Jupiter has the sun. Yet throughout the galaxy, there may be billions of worlds that belong to no star at all. Astronomers call them rogue planets. These lonely wanderers drift through interstellar space, moving through the darkness between stellar systems with no permanent source of light and no home to orbit. And strangely enough, some of them may be among the most fascinating worlds in the universe. The idea of rogue planets once sounded almost absurd. For much of human history, planets were defined by their relationship to stars. They formed around stars. They orbited stars. Their existence seemed inseparable from the brilliant suns that illuminated them. But modern astronomy has revealed a far more dynamic and chaotic universe. Planetary systems are not always stable places. Young solar systems can be crowded and turbulent. Giant planets pull on one another. Orbits shift. Gravitational encounters reshape entire systems. Sometimes one world loses. A close encounter with a massive neighboring planet can act like a cosmic slingshot. Instead of remaining safely in orbit, a smaller world may be flung outward with enormous speed. The planet escapes its star's gravitational grasp and begins a journey that may continue for billions of years, never returning, never slowing down, simply wandering through the galaxy alone. It is a remarkably dramatic fate. Entire planets can be evicted from their birthplaces. Worlds that once circled warm stars may suddenly find themselves cast into a darkness deeper than anything we can easily imagine. And this process may not be rare. Computer simulations suggest that many planetary systems experience periods of instability during their early history. Some planets collide, some migrate inward, and some are ejected completely. If this happens often enough across the Milky Way, rogue planets could actually outnumber the stars themselves. That possibility changes how we imagine our galaxy. When we look at the night sky, we see hundreds of billions of stars. But hidden between them may be an even larger population of invisible worlds, silent travelers moving through the darkness. Most would be nearly impossible to detect. After all, planets do not produce their own visible light. Without a nearby star illuminating them, rogue planets become extraordinarily faint. They disappear into the cosmic night. Yet astronomers have still managed to find some of them. One technique relies on a phenomenon known as gravitational microlensing. According to Einstein's theory of general relativity, mass bends spacetime. When a rogue planet passes in front of a distant star, its gravity can briefly magnify the starlight behind it. The effect may last only hours or days. Then the planet continues on its way, vanishing once more into darkness. These fleeting events have provided some of the strongest evidence that rogue planets truly exist. And every detection hints at many more waiting unseen. But perhaps the most fascinating question is not how many rogue planets exist. It is what conditions might exist on them. At first glance, such worlds seem hopelessly frozen. Without sunlight, temperatures would plunge. Any surface oceans would freeze solid. The landscape might become buried beneath vast sheets of ice. The environment would appear completely hostile to life. Yet the universe has a way of surprising us. Even without sunlight, planets can possess internal heat.
Deep beneath their surfaces, radioactive elements slowly decay. The heat generated by this process can persist for billions of years. On Earth, radioactive heating helps drive geological activity even today. A rogue planet could experience the same effect. Now imagine a large planet with a thick atmosphere, perhaps one rich in hydrogen. Such an atmosphere could act as an insulating blanket, trapping heat that escapes from the planet's interior.
Remarkably, some theoretical studies suggest that under the right conditions, liquid water could potentially exist beneath the surface, despite the absence of sunlight. Not on the surface, but hidden below layers of ice, protected from the cold vacuum above. The image is extraordinary. A dark world wandering between stars, frozen on the outside, yet potentially harboring warm oceans deep below. It sounds almost like science fiction, and yet it emerges naturally from known physics. Some scientists have even speculated that rogue planets could offer surprisingly stable environments for microbial life. Life would not depend on a star. Instead, it would rely on internal heat and chemical energy. In such a scenario, a planet drifting alone through interstellar space might remain habitable far longer than many planets orbiting stars. Stars eventually change. They brighten, they die, they explode. But a rogue planet could continue drifting quietly through the galaxy for unimaginable spans of time. The darkness itself becomes strangely comforting. No solar flares, no stellar instability, just slow, steady existence beneath layers of ice. Of course, we do not yet know whether any rogue planet actually hosts life. The evidence simply is not there, but the possibility expands our imagination. It reminds us that life, if it exists elsewhere, may not always follow the patterns we expect. Perhaps habitability is broader than we once believed. Perhaps warmth can survive in places where sunlight never reaches. And perhaps the galaxy contains hidden refuges scattered throughout the darkness. The scale of these journeys is almost impossible to comprehend. A rogue planet may travel for millions or even billions of years. It could drift through spiral arms of the galaxy, past distant nebulae, cross regions filled with stars, then enter vast empty spaces where the nearest sun is dozens of light years away. Throughout all of it, the planet remains alone. Yet there is something strangely peaceful about that image. A solitary world moving silently through the Milky Way, not racing toward a destination, not following a grand mission, simply continuing onward through the cosmic night. Perhaps that is part of what makes rogue planets so captivating. They challenge our assumptions about what a world can be. They reveal that planets are not always tied to stars. They show that darkness does not necessarily mean emptiness, and they remind us that the universe is far more inventive than our first ideas often suggest. Tonight, as we continue our quiet journey through the cosmos, it is worth remembering that somewhere out there, beyond the familiar constellations, countless unseen worlds may be drifting through eternal darkness. Invisible, silent, ancient, carrying their own stories through the vast spaces between the stars. And perhaps in that endless night, they are teaching us one of astronomy's most beautiful lessons. Even the loneliest places in the universe can still hold wonder. Imagine sitting beneath a quiet night sky and suddenly receiving a signal so powerful that for a fraction of a second, it releases as much energy as the sun produces over many days. The signal arrives without warning. It lasts only an instant, and then it is gone. For years, astronomers have detected brief flashes of radio energy so powerful that they can outshine entire galaxies. These events are known as fast radio bursts, often shortened to FRBs. And despite years of observation, they remain among the most fascinating mysteries in modern astronomy. The story began in 2007, when researchers studying old telescope data discovered something unusual. Hidden within recordings from several years earlier was a single, incredibly bright pulse of radio waves. The signal lasted only milliseconds. At first, many scientists wondered whether it might be an error. Perhaps it came from human technology. Perhaps it was interference from Earth. But as more observations accumulated, similar bursts continued appearing. The strange flash had not been a mistake. It was the first glimpse of an entirely new cosmic phenomenon. Since then, astronomers have detected thousands of fast radio bursts. Some appear only once and never return. Others repeat again and again from the same region of space. Each new detection adds another clue.
Yet the overall puzzle remains remarkably difficult to solve. Part of the challenge comes from their brevity. Imagine trying to understand the source of a lightning strike when you can only see a single flash lasting less than a blink. That is the situation astronomers often face. By the time telescopes notice the signal, the event has already ended. Only a tiny fingerprint remains. From that fingerprint, researchers must reconstruct an entire cosmic story. And what a story it may be. Many fast radio bursts originate from unimaginably distant galaxies. The radio waves travel for millions or even billions of years before reaching Earth. Their journey carries them across enormous stretches of intergalactic space. Along the way, the signals pass through clouds of gas, magnetic fields, and regions of plasma. Each obstacle slightly alters the radio waves. By carefully measuring those changes, astronomers can learn about the invisible material scattered throughout the universe. In a surprising way, these mysterious bursts have become valuable scientific tools. The signals are not only mysteries themselves, they also help reveal other mysteries. One of the most fascinating aspects of FRBS is their incredible brightness. Radio waves are normally quite weak by the time they reach Earth from distant galaxies, yet fast radio bursts remain detectable across cosmic distances. Whatever creates them must be extraordinarily energetic. The source compresses an immense amount of power into an incredibly short moment. This requirement immediately eliminates many ordinary explanations. Stars like our Sun cannot produce such events. Planets cannot produce them. The mechanisms must involve some of the most extreme environments in the universe. One leading explanation points toward magnetars. A magnetar is a special kind of neutron star. Neutron stars themselves are already extraordinary. They form when massive stars explode as supernovae and collapse into objects only a few kilometers wide. Despite their small size, they can contain more mass than the Sun. A teaspoon of neutron star material would weigh billions of tons. Magnetars take this concept even further. They possess magnetic fields so powerful that they challenge ordinary imagination. If one were placed halfway between Earth and the Moon, its magnetic field could disrupt electronic systems across our planet. When stresses build within a magnetar's crust, enormous bursts of energy may erupt. Some scientists believe these violent outbursts could generate fast radio bursts. This idea gained support in 2020 when astronomers observed a magnetar within our own galaxy, producing a radio burst remarkably similar to the mysterious events seen elsewhere. It was not definitive proof, but it provided one of the strongest clues yet. Still, the mystery is far from solved. Not all fast radio bursts behave the same way. Some repeat frequently, others appear only once. Certain bursts occur in regions rich with star formation. Others originate from much older environments. The diversity suggests that multiple mechanisms may be involved. Perhaps different cosmic objects can create similar signals. Nature often surprises us in exactly this way. Just when a mystery seems close to resolution, it becomes more complicated. For a brief period, public imagination raced toward another possibility. Could these signals be artificial? Could they be evidence of advanced civilizations? The idea captured headlines because the bursts seem so powerful and unusual. Scientists always remain open to possibilities supported by evidence. However, most researchers currently favor natural explanations. The signals show characteristics that fit known astrophysical processes more comfortably than technological origins. Yet the discussion itself reveals something important. Fast radio bursts are strange enough that they invite us to consider possibilities stretching far beyond ordinary experience. They remind us how little we still know. Perhaps the most beautiful aspect of these signals is what they reveal about cosmic distance. When an FRB reaches Earth, it has often been traveling for unimaginable spans of time. The burst may have left its home galaxy before humanity built cities, before written language emerged, sometimes before our species even existed. The signal crosses the darkness between galaxies, while stars are born and die, while planets form and vanish, while entire civilizations rise and fall. Then, after billions of years of travel, it briefly touches a radio telescope on Earth. A journey lasting longer than human history concludes in a fraction of a second. There is something deeply humbling about that thought. These fleeting flashes also help astronomers map the hidden universe. For decades, scientists struggled to locate some of the normal matter predicted by cosmological models. Much of it seemed missing. FRBs have helped track down portions of this elusive material. As the radio waves travel through intergalactic gas, they slow slightly in measurable ways. By studying these delays, researchers can estimate how much matter lies between galaxies. The bursts become probes of invisible structure. They illuminate regions that would otherwise remain difficult to study. In this way, a mystery becomes a tool for solving other mysteries. The universe often works like that. Questions lead to discoveries. Those discoveries reveal deeper questions. And the journey continues. Every year, new observatories detect more fast radio bursts than ever before. Modern instruments scan the sky continuously, catching signals that earlier generations would have missed. Patterns are beginning to emerge. Catalogs are growing. The picture is becoming clearer. Yet the full explanation still remains just beyond reach. And perhaps that uncertainty is part of the appeal. A universe with no mysteries would be far less interesting. Fast radio bursts remind us that even today, with powerful telescopes orbiting Earth and giant observatories spread across continents, nature still keeps secrets. Some of those secrets arrive as whispers, others arrive as flashes. For a few thousandths of a second, a distant galaxy sends a message across billions of years of darkness. Not a message written in words, not a signal carrying intention, but a burst of energy, revealing that somewhere in the vast cosmos, something extraordinary has happened. And as we continue listening to the sky, those brief flashes may eventually teach us not only about neutron stars, magnetic fields, and distant galaxies, but about the hidden structure of the universe itself. For now, the signals continue to arrive. Short, powerful, mysterious. Tiny sparks from the deep darkness between the stars. And each one reminds us that the universe still has many stories left to tell. Some ideas in modern theoretical physics suggest that black holes may be far more than cosmic traps. Instead of being simple endpoints where matter disappears from view, they might be connected to processes that create entirely new regions of reality. It is an extraordinary possibility, one that remains speculative, but it invites us to think about black holes in a very different way. At first glance, black holes seem like the ultimate destroyers. A massive star exhausts its fuel. Gravity wins. The star collapses inward. An event horizon forms. Anything crossing that boundary can no longer communicate with the outside universe. From the perspective of an observer far away, a black hole appears to be a one-way destination. Matter falls in, light falls in, information seems to vanish. For decades, this picture made black holes feel like cosmic endings. Yet the deeper physicists studied them, the stranger they became. Black holes turned out not to be simple holes at all. They possess temperature. They can slowly evaporate through a process known as Hawking radiation. They contain enormous amounts of entropy. And perhaps most intriguingly, the mathematics describing their interiors leads toward regions where our current understanding of physics breaks down completely. At the center of a traditional black hole model lies something called a singularity. A singularity is not necessarily a physical object. Rather, it is a place where the equations of general relativity produce infinite density and infinite curvature. Whenever infinities appear in physics, scientists become suspicious. Infinite values usually signal that a theory has reached the limits of its usefulness. It does not necessarily mean nature itself contains infinities. Instead, it often means we are missing a deeper description. The singularity inside a black hole may be one of the clearest signs that our understanding remains incomplete. And that gap in knowledge is where some of the most fascinating ideas emerge. One possibility is that the singularity never truly forms. Perhaps at incredibly small scales, quantum effects become powerful enough to stop complete collapse. Instead of crushing matter into an infinitely dense point, the laws of nature may trigger a different process entirely. Some researchers have imagined a kind of cosmic rebound. Matter collapses inward under gravity. Density rises to extraordinary levels. Then quantum physics intervenes. The collapse halts. A new expansion begins. In this picture, what appears from the outside as a black hole might contain an entirely new expanding region of space on the inside, a universe born from collapse. The idea sounds almost like science fiction, yet it emerges naturally from attempts to combine general relativity with quantum mechanics. And while no evidence currently confirms such a scenario, the mathematics is intriguing enough that physicists continue exploring it.
Imagine standing inside a universe created this way. You would not see yourself living inside a black hole. Everything around you would appear normal. Galaxies would form, stars would ignite, planets would emerge. Observers would measure their own expanding cosmos. They might even develop theories about a beginning event remarkably similar to what we call the Big Bang. From their perspective, their universe would simply exist. The parent universe would remain hidden forever. This idea leads to a remarkable question. Could our own universe have originated inside a black hole existing within another cosmos? It is impossible to know, at least for now, but the thought carries a strange elegance. Instead of a universe appearing from absolute nothingness, one universe could give rise to another. Creation emerging from collapse. Birth emerging from destruction. The most violent objects in existence becoming cosmic seeds. Some versions of this concept are associated with what is sometimes called cosmological natural selection. The proposal suggests that universes capable of producing many black holes might generate more offspring universes. Over unimaginably long periods, certain physical laws could become more common because they favor black hole production. The analogy resembles biological evolution, though operating on cosmic scales. Again, this remains highly speculative. No observational evidence currently supports it, but it demonstrates how black holes continue to inspire new ways of thinking about reality. What makes these ideas so captivating is that black holes already blur the boundaries between seemingly separate areas of physics. They connect gravity, thermodynamics, quantum mechanics, information theory, and cosmology. Few objects occupy so many scientific frontiers simultaneously. Every time researchers investigate them deeply, new mysteries seem to emerge. Even the event horizon itself raises profound questions. According to some modern theories, information that falls into a black hole may not truly disappear. Instead, it could somehow be encoded on the horizon's surface. Others suggest reality may possess holographic properties, where information contained within a volume can be described on a lower dimensional boundary. These concepts sound astonishingly abstract, yet they arise from serious attempts to solve fundamental puzzles. And remarkably, black holes sit at the center of many of them. The possibility of universe creation also changes how we emotionally perceive these objects. Traditionally, black holes feel dark. They swallow, they erase, they trap. But if there is even a grain of truth in some of these theories, black holes might also represent beginnings, a place where one story ends and another begins beyond our view, a gateway not through space, but through cosmic history. Of course, caution is essential. Scientists have not observed a baby universe emerging from a black hole. No telescope has detected evidence proving that our cosmos was born inside one. These ideas remain theoretical explorations rather than established facts. The distinction matters. Science advances through evidence. Speculation becomes knowledge only when observations support it. Yet there is value in exploring possibilities, especially when those possibilities help illuminate where current theories succeed and where they fall short. In many ways, black holes serve as laboratories of imagination, guided by mathematics. They reveal the edges of what we know, and at those edges, extraordinary questions naturally arise. Perhaps that is why black holes continue to fascinate us more than a century after Einstein first described the gravitational framework that made them possible. They are not merely objects in space. They are invitations to think beyond familiar limits. Could black holes create new universes? Today, nobody knows. The answer may ultimately be yes. It may be no, or reality may turn out to be stranger than either possibility. What we do know is that black holes force us to confront some of the deepest mysteries in existence. They challenge our understanding of space, time, matter, information, and origins themselves. And somewhere beyond those mysteries may lie a truth more astonishing than anything we have yet imagined. As you picture those silent dark spheres scattered across the cosmos tonight, perhaps they can seem a little different. Not merely as endings, not merely as cosmic prisons,
but as reminders that even the darkest places in the universe may still be hiding possibilities we have not yet learned how to see. The earliest chapters of the universe contain one of the greatest mysteries in modern astronomy. Today, astronomers routinely observe black holes weighing millions or even billions of times more than our sun. Many sit quietly at the centers of galaxies, while others blaze with extraordinary brightness as they consume surrounding matter. Yet when scientists look far back in time, toward the young universe only a few 100 million years after the Big Bang, they encounter something deeply puzzling. Some of these enormous black holes were already there. And that raises a question that sounds almost impossible. How did something so massive grow so quickly? To appreciate the mystery, it helps to imagine cosmic time on a human scale. The universe is approximately 13.8 billion years old. If that entire history were compressed into a single calendar year, the first giant black holes would appear astonishingly early, long before galaxies had settled into the familiar forms we see today. In those ancient eras, the cosmos was still young. The first generations of stars were only beginning to shine. Galaxies were still assembling themselves from clouds of gas and dark matter. And yet somehow, hidden within this youthful universe, colossal black holes already existed. Astronomers first discovered clues to these giants through objects called quasars. Quasars are among the brightest things in the entire universe. At first glance, they resemble stars. In fact, the word quasar originally came from the phrase quasi-stellar radio source. But quasars are not stars at all. They are powered by supermassive black holes, feeding at incredible rates. As gas spirals toward a black hole, it forms a rapidly rotating disk known as an accretion disk. Friction heats this material to extraordinary temperatures, causing it to radiate tremendous amounts of energy. The result is astonishing. A region no larger than our solar system can outshine an entire galaxy containing hundreds of billions of stars. When astronomers use powerful telescopes to look billions of light years away, they are also looking billions of years into the past. And there, in the distant darkness, they find quasars, shining from an era when the universe was surprisingly young. Some of these quasars appear less than 1 billion years after the Big Bang. Their central black holes already contain masses equivalent to billions of suns. That is where the puzzle begins. Black holes do not simply appear fully grown. They must form somehow, and they must gain mass somehow. The simplest explanation begins with stars. When massive stars exhaust their nuclear fuel, they can collapse under their own gravity and form black holes. Many stellar black holes weigh only a few times more than our sun. Some are larger. But even a black hole containing 100 solar masses faces an enormous challenge if it hopes to become a billion solar mass giant. Growing from 100 to 1 billion is not a small step. It is an almost unimaginable leap. Black holes gain mass by consuming surrounding material. Gas falls inward. Stars occasionally wander too close. Mergers combine multiple black holes into larger ones. But these processes have limits. Matter cannot simply fall into a black hole infinitely fast. Radiation produced during accretion pushes outward and can slow the inflow of additional material. This creates a natural speed limit known as the Eddington limit. According to conventional growth models, many early supermassive black holes seem to have grown faster than expected. They reached enormous sizes before there should have been enough time available. It is almost as though someone discovered fully grown oak trees in a landscape where the first acorns had only recently fallen. Naturally, astronomers began searching for alternative explanations. Perhaps the seeds themselves were much larger. Instead of starting from ordinary stellar remnants, some researchers proposed that enormous clouds of primordial gas may have collapsed directly into black holes. These hypothetical objects are called direct collapse black holes. Unlike normal black holes formed by dying stars, direct collapse black holes could begin life already containing tens of thousands or even hundreds of thousands of solar masses. Such a head start would make the growth problem far easier. The black hole would not need to climb the entire ladder. It would begin halfway up. The idea is elegant, yet proving it remains difficult. The early universe left few clear records. Much of the evidence lies hidden behind immense distances and immense stretches of time. Astronomers continue searching for observations that might reveal whether direct collapse black holes truly existed. Another possibility involves periods of extraordinarily rapid feeding. Perhaps some young black holes briefly exceeded the normal growth limits. In certain environments, dense gas clouds might have delivered vast quantities of material faster than standard models predict. These episodes could have allowed black holes to gain mass at remarkable rates. The universe, after all, is not always orderly, especially in its youth. The early cosmos was a place of turbulence, collisions, and rapid transformation. Galaxies merged frequently. Gas flowed along invisible cosmic filaments. Star formation erupted across enormous regions. Under such extreme conditions, black holes may have found unusually rich supplies of fuel. There is also the possibility that multiple processes worked together. Perhaps large seeds formed first, then rapid feeding accelerated growth. Then repeated mergers added still more mass. Nature rarely relies on a single mechanism. The universe often solves problems through combinations of many different processes, acting over long periods of time. What makes this mystery especially fascinating is that it touches almost every major area of cosmology. To understand giant black holes, astronomers must understand early stars. They must understand galaxy formation. They must understand dark matter. They must understand how gas behaved during the first billion years of cosmic history. Each discovery connects to countless others. The mystery of cosmic giants is therefore not merely a question about black holes. It is a question about how structure emerged throughout the universe itself. The recent observations from the James Webb Space Telescope have made this puzzle even more intriguing. Webb is allowing astronomers to peer deeper into cosmic history than ever before. Some of the galaxies observed in the young universe appear surprisingly mature. Some contain evidence of significant structure and rapid growth. The deeper scientists look, the more complex the early cosmos appears. Rather than a simple and gradual beginning, the universe increasingly resembles a place capable of remarkable feats of construction very early in its history. That realization is both exciting and humbling. For many years, astronomers expected the first galaxies and black holes to grow slowly. Instead, observations continue to suggest a universe capable of astonishing efficiency. Massive structures emerged quickly. Stars formed rapidly. Galaxies assembled themselves. And somewhere among them, giant black holes rose to enormous sizes in what seems like the blink of a cosmic eye. Perhaps future observations will reveal the answer. Perhaps hidden populations of intermediate black holes will fill in the missing steps. Perhaps entirely new physical processes remain waiting to be discovered. Or perhaps the universe will surprise us once again with an explanation more imaginative than any current theory. That possibility is part of what makes astronomy so captivating. Every mystery solved often reveals several new mysteries behind it. The giant black holes of the young universe remind us that the cosmos still guards many secrets. They sit at the crossroads of gravity, time, light, and cosmic evolution. Silent, invisible, yet powerful enough to illuminate entire galaxies. And as we continue looking deeper into space, we are also looking deeper into the past, searching for the moment when these cosmic giants first emerged from the darkness. Somewhere in those ancient epochs, hidden among the first stars and newborn galaxies, lies the answer to one of the universe's greatest questions. How did the giants grow so fast? For now, the mystery remains. And perhaps that is what makes it so beautiful. The first stars occupy a special place in cosmic history because they mark the moment when the universe began transforming itself into something far more complex than it had been before. Before their birth, the cosmos was a remarkably simple place. There were no planets, no galaxies like the Milky Way, no rocky worlds, no oceans, no trees, no animals. No people looking up at the night sky. There was mostly hydrogen, helium, dark matter, and vast stretches of darkness. The ingredients for future complexity existed, but they had not yet been assembled into the structures we recognize today. That is why astronomers often describe the appearance of the first stars as the end of the cosmic dark ages. The phrase sounds dramatic, but it is surprisingly accurate. For hundreds of millions of years after the Big Bang, the universe contained no stars at all. Space was not completely black. There was still ancient radiation left over from the Big Bang itself, yet there were no stellar beacons illuminating the darkness. The cosmos waited. Gravity continued its quiet work. Tiny fluctuations left behind from the earliest moments of cosmic history slowly grew larger. Regions containing slightly more matter attracted even more matter. Clouds became denser. Dark matter gathered into enormous halos. Gas followed. And eventually, in certain locations, conditions became extreme enough for the first stars to ignite. What those first stars looked like remains one of the most fascinating mysteries in astronomy. They were probably very different from the stars we see around us today. Modern stars form from gas clouds that contain many chemical elements: carbon, oxygen, silicon, iron, and dozens of others. But the first stars had none of these. The universe had not yet manufactured them. Only hydrogen and helium existed in significant amounts. That simple chemistry likely changed everything. Without heavier elements to help cool collapsing gas clouds, early star-forming regions may have behaved differently from modern ones. Many astronomers suspect the first stars were enormous. Some models suggest masses dozens or even hundreds of times greater than our Sun. If true, these ancient giants would have burned with incredible brightness. Their lives would have been short, violent, and transformative. The irony is beautiful. The first stars may have lived only a tiny fraction of the lifespan enjoyed by smaller stars today, yet their brief existence changed the future of the entire universe. Massive stars consume their fuel rapidly. They shine intensely. They generate powerful radiation, and eventually, many end their lives in spectacular explosions. Those explosions were not merely dramatic events, they were acts of cosmic creation. Inside the cores of stars, new elements are forged through nuclear fusion. Hydrogen becomes helium. Helium helps create carbon. Carbon leads toward oxygen and heavier elements. The process continues until the star can no longer support itself. When the largest stars die, they scatter those newly created elements into surrounding space. Before the first stars existed, the universe lacked most of the ingredients necessary for planets and life. After they died, those ingredients began spreading across the cosmos. Every atom of oxygen you breathe, every atom of calcium in your bones, every atom of iron in your blood, all were ultimately forged inside stars. That realization gives the search for the first stars an almost poetic significance. Astronomers are not merely hunting ancient objects. They are searching for the beginning of a chain of events that eventually made their own existence possible. In a sense, the first stars were the universe's first great act of self-transformation. They altered the chemistry of space. They illuminated the darkness. They helped galaxies grow. They influenced everything that followed. Another reason the first stars matter so deeply involves something called cosmic reionization. This may sound complicated, but the basic idea is surprisingly simple. After the Big Bang, atoms eventually formed and filled space with neutral hydrogen gas. This gas absorbed certain kinds of light very effectively. The universe became somewhat foggy on cosmic scales. Then the first stars appeared. Their intense ultraviolet radiation began stripping electrons away from surrounding hydrogen atoms. Little by little, bubbles of ionized gas expanded outward. Over time, these bubbles grew larger and merged together. Eventually, much of the universe became transparent once again. The cosmic fog lifted. Light could travel more freely across enormous distances. The universe became easier to see through. This transformation ranks among the most important events in cosmic history, yet many details remain uncertain. Exactly when did it happen? How quickly did it unfold? How much of the process was driven by the first stars? How much came from early galaxies and growing black holes? These questions continue to motivate some of the most ambitious astronomical observations ever attempted. This is where modern telescopes enter the story. The search for the first stars is incredibly difficult because of one unavoidable problem: distance. The farther away an object lies, the longer its light takes to reach us. The first stars existed more than 13 billion years ago. Any light from that era has traveled across almost the entire age of the universe. By the time it reaches Earth, it is extraordinarily faint. Even worse, cosmic expansion stretches that light into longer wavelengths. Much of it arrives as infrared radiation rather than visible light. For decades, astronomers lacked the tools needed to explore this ancient frontier properly, but newer observatories are changing that.
The James Webb Space Telescope was specifically designed to peer deeper into cosmic history than ever before. Its powerful infrared instruments allow scientists to detect some of the earliest galaxies yet discovered. These observations are bringing researchers closer to the era when the first stars likely appeared. So far, astronomers have not directly identified a confirmed first-generation star, but they are finding galaxies that existed astonishingly early. Each new discovery narrows the search. Each observation pushes the frontier farther back. Each ancient galaxy becomes another clue. Some scientists hope that future observations may reveal stars formed almost entirely from primordial hydrogen and helium. Others believe we may instead find their fingerprints indirectly through chemical signatures preserved in later generations of stars. Either outcome would be remarkable, because sometimes science advances not by finding exactly what we expected, but by uncovering evidence that points toward hidden chapters of history. And perhaps that is what makes the first stars so captivating. They sit at the edge of visibility, at the border between knowledge and mystery. They are among the earliest actors in a cosmic story that eventually led to galaxies, planets, oceans, and life itself. Tonight, as we imagine those ancient stars flickering into existence across a young and dark universe, it becomes easier to appreciate how much of cosmic history depends on events we can barely observe. The first stars may have vanished billions of years ago. Their light may be incredibly difficult to detect. Their identities may still remain uncertain. Yet their influence surrounds us everywhere. The atoms they helped create are woven into galaxies, into planets, into living creatures, and into every person who has ever looked up at the night sky and wondered how it all began. If you're still awake beneath the stars, take a moment to subscribe so you won't miss future cosmic bedtime journeys. And as tonight's voyage continues, let your thoughts drift back to that ancient age when the first lights appeared in the darkness, quietly beginning a story that is still unfolding across the universe today. The silence is what makes the question so unsettling. Every night, as Earth turns beneath the stars, our planet drifts through a galaxy containing hundreds of billions of suns. Beyond the Milky Way lie hundreds of billions of other galaxies, each filled with worlds, moons, oceans, atmospheres, and possibilities beyond counting. And yet, no voices arrive from the darkness. No unmistakable messages. No giant structures orbiting distant stars. No clear evidence that another technological civilization is reaching across the cosmic sea. The universe appears astonishingly capable of producing life, yet it remains astonishingly quiet. This mystery has haunted astronomers, physicists, and dreamers for generations. It is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked a simple question during a conversation about extraterrestrial life. Where is everybody? The question sounds almost casual, but hidden inside it is one of the deepest puzzles in modern science. Because when we begin looking at the numbers, the silence becomes difficult to explain. The Milky Way is more than 13 billion years old. Our sun is relatively young. Many stars formed billions of years before our own solar system existed. If intelligent life can arise naturally, then some civilizations could theoretically have had enormous head starts. Not hundreds of years, not thousands, but millions or even billions of years. A civilization with that much extra time might achieve technologies far beyond anything humanity can currently imagine. Even traveling slowly compared with the speed of light, such a civilization could potentially spread across large portions of a galaxy over immense spans of time. And yet when we point our telescopes toward the heavens, we do not see obvious evidence of galaxy-spanning empires. The sky remains strangely ordinary. This is where the paradox begins. The universe seems large enough to make intelligent life likely, but observations so far provide no clear confirmation that advanced civilizations are common. Somewhere between those two ideas lies a missing piece of the story. Perhaps intelligent life is extraordinarily rare. After all, life on Earth may have required an astonishing chain of fortunate events. A stable star, a rocky planet, liquid water, protective magnetic fields, the right chemical ingredients, enough time for evolution to perform its slow work. Even then, complex life took billions of years to appear, and technological civilization emerged only within the tiniest fraction of Earth's history.
Maybe the path from simple organisms to intelligent beings is far more difficult than it seems. If so, humanity could be one of the very few civilizations currently active in our galaxy. That possibility feels lonely, but it also feels strangely remarkable. It would mean that conscious minds capable of wondering about the universe may be among its rarest creations. Another possibility is even more intriguing. Perhaps intelligent civilizations appear frequently, but they do not last very long. This idea introduces what researchers sometimes call the Great Filter, a stage in development so difficult that most civilizations never successfully pass through it. The filter could exist in the distant past. Maybe life rarely begins. Maybe complex cells almost never evolve. Maybe intelligence is exceptionally uncommon. If that is true, then humanity may have already crossed the hardest obstacles. But there is another possibility. The filter may lie ahead. Civilizations might develop technology powerful enough to transform their worlds, yet they may also develop risks capable of ending their progress. Environmental collapse, resource depletion, uncontrolled technologies. Unknown dangers we have not yet encountered. If most civilizations eventually destroy themselves, the galaxy could remain quiet not because life is rare, but because survival is difficult. It is a sobering thought, yet it reminds us that intelligence alone may not guarantee longevity. Wisdom could be just as important. There is also the possibility that advanced civilizations simply choose not to announce themselves. Humanity often assumes that alien societies would want communication, but that assumption reflects human expectations. A civilization millions of years older than ours might have goals, values, and interests completely unlike anything we understand. They may communicate in ways we cannot detect. They may inhabit virtual worlds. They may focus inward rather than outward, or perhaps they deliberately remain silent. Some researchers compare this idea to animals living deep within a forest. The animals may not understand the activities of human observers nearby. Likewise, humanity could be surrounded by phenomena that appear ordinary, simply because we lack the knowledge to recognize them. The universe may not be empty. It may simply be speaking a language we have not yet learned. The search itself has become one of humanity's most fascinating scientific efforts. For decades, astronomers have listened for signals from distant stars. Large radio telescopes scan the sky, searching for patterns that nature would struggle to produce on its own. The effort is patient, quiet, methodical. Most observations reveal only natural cosmic sources: pulsars, galaxies, interstellar gas, the familiar whispers of the universe. Yet the search continues, because finding even a single confirmed signal would instantly change our understanding of life forever. One message, one unmistakable transmission, one piece of evidence that another intelligence exists. That would be enough. The discovery would rank among the most important moments in human history. But there is another possibility that feels surprisingly beautiful. Perhaps civilizations are separated not by distance alone, but by time. The universe is ancient. Civilizations may rise and fall across millions of years. One species could flourish long before another appears. Entire cultures might bloom and disappear before their successors even begin evolving. The galaxy could be filled with histories that never overlap, worlds separated not only by space, but by eras. In that picture, the silence becomes less mysterious. It becomes a consequence of cosmic timing. Two civilizations might exist within the same galaxy, yet miss each other completely, like ships passing through an ocean thousands of years apart. This perspective transforms the night sky. Every star becomes a possibility. Every distant sun could possess a story we will never know. An ocean world beneath icy clouds, a desert planet beneath a red sun, a civilization that flourished millions of years ago, or one that has not yet begun. The silence does not necessarily mean nothing is there. Sometimes silence simply means the conversation has not happened yet, and perhaps that is why the search remains so captivating. Not because we expect easy answers, but because the question itself invites wonder. Each new telescope, each new exoplanet discovery, each new observation of distant worlds adds another piece to a puzzle that humanity has only recently begun exploring. The universe remains vast, patient, unimaginably old.
Somewhere beyond the reach of our current knowledge may lie the answer to one of the greatest mysteries ever asked. Are we alone? Tonight, no one knows, but the search continues. And as Earth drifts quietly through the darkness beneath billions of stars, the silence itself remains part of the story. A vast and beautiful mystery stretching across the galaxy, waiting, perhaps, for someone to answer. The mystery of dark matter begins with something surprisingly simple. Astronomers looked at galaxies and tried to weigh them. At first, this seems straightforward. Count the stars, measure the gas, estimate the dust, add everything together. The result should tell you how much matter exists inside a galaxy and how strong its gravity should be. But when scientists began measuring how fast stars moved around galactic centers, something strange appeared. The numbers refused to agree. Stars near the outer edges of galaxies were moving far too quickly. According to the visible matter alone, those stars should not have been able to maintain their orbits. They should have drifted away into intergalactic space long ago. Yet they remained, again and again, galaxy after galaxy. No matter where astronomers looked, the same puzzle emerged. It was as though an invisible mass surrounded every galaxy, providing extra gravity that nobody could see. At first, many researchers suspected mistakes. Perhaps the measurements were wrong. Perhaps some aspect of stellar motion was misunderstood. Perhaps there were unseen clouds of gas hiding between the stars. But as observations improved over decades, the mystery only deepened. The evidence became impossible to ignore. Something invisible appeared to be shaping the cosmos. And whatever it was, there seemed to be far more of it than ordinary matter. This realization quietly transformed modern astronomy. Today, scientists estimate that all the stars, planets, moons, gas clouds, nebulae, black holes, and galaxies we can directly observe account for only a small fraction of the universe's total matter content. Most of the matter appears to be something else entirely. Something dark, something unseen, something that does not interact with light the way normal matter does. And yet, its gravity influences nearly everything. When you look up at the night sky, every star you can see belongs to the familiar world of ordinary matter. The atoms in your body, the oxygen you breathe, the rocks beneath your feet, the oceans, the sun, everything that feels tangible and real. All of it belongs to a surprisingly small category. The overwhelming majority of matter in the cosmos seems to exist beyond direct visibility. That idea can feel almost unbelievable. Human beings evolved in a universe where sight often serves as our primary guide. We trust what we can observe. We believe what we can touch. Yet astronomy repeatedly reminds us that reality is not obligated to reveal itself so easily. In fact, some of the most important components of the universe may be invisible. Dark matter reveals itself not through light, but through influence. It leaves fingerprints rather than photographs. And those fingerprints appear everywhere. One of the strongest clues comes from galaxy clusters. A galaxy cluster is among the largest structures in existence. Hundreds or even thousands of galaxies can be bound together by gravity. When astronomers calculated how much visible matter existed within these clusters, they encountered another discrepancy. The galaxies were moving too fast, far too fast. Without additional mass, the clusters should have flown apart, yet they remained gravitationally bound. Something unseen seemed to be holding them together. This observation dates back nearly a century. In the 1930s, Swiss astronomer Fritz Zwicky noticed this very problem while studying the Coma cluster. His calculations suggested that enormous amounts of missing mass existed within the cluster. At the time, the idea seemed so strange that many scientists remained skeptical. But decades later, new evidence would point in the same direction, and then more evidence, and more. The mystery kept returning, like a shadow that refused to disappear. Another remarkable clue comes from gravitational lensing. According to the theory of relativity, gravity can bend the path of light. Massive objects distort space-time itself. As light travels through that curved space-time, its path changes. This effect allows astronomers to weigh distant objects using light alone. When researchers examined many galaxies and clusters through gravitational lensing, they discovered something astonishing. Visible matter could not account for the amount of lensing observed.
The distortions were stronger than expected. The invisible mass was there again, not seen directly, but revealed through its gravitational effects. In a sense, dark matter behaves like a hidden landscape. Imagine walking through a fog-covered valley at night. You cannot see the hills, you cannot see the mountains, yet you can infer their presence from the way rivers flow around them. Dark matter may be similar. We do not see the object itself. We see how everything else responds to it. The galaxies become the rivers, gravity becomes the map, and the invisible terrain slowly emerges. One of the most fascinating discoveries came from observations of galaxy collisions. When galaxy clusters crash together, ordinary matter behaves differently from dark matter. Gas clouds collide. They slow down, they heat up, they emit X-rays. Dark matter appears to pass through relatively unaffected. These cosmic collisions provide rare opportunities to separate visible matter from invisible matter. In some famous observations, astronomers found that most of the gravitational mass was located in regions where very little ordinary matter existed. The result was striking. It suggested that dark matter is not simply hidden gas or faint stars. It appears to be something fundamentally different, something that interacts weakly with ordinary matter while still exerting gravity. Despite decades of research, scientists still do not know exactly what dark matter is. That may be one of the most extraordinary aspects of the mystery. We can map its influence across billions of light years. We can estimate its abundance. We can watch it shape galaxies. We can observe its role in cosmic evolution. Yet its true nature remains elusive. Many candidates have been proposed: exotic particles, weakly interacting massive particles, axions, primordial remnants from the early universe, entirely new forms of physics. Laboratories around the world have searched for direct evidence. Massive detectors have been placed deep underground to shield them from interference. Powerful particle accelerators have hunted for clues. Space-based observatories continue searching. So far, definitive answers remain out of reach. And perhaps that uncertainty is part of what makes dark matter so captivating. It reminds us that even after centuries of scientific progress, enormous mysteries still surround us. The universe remains larger than our understanding, deeper than our models, more creative than our assumptions. Dark matter also played a crucial role in shaping the universe itself. Without it, galaxies may never have formed the way they did. In the early universe, tiny density fluctuations existed within the cosmic landscape. Dark matter's gravity helped amplify those fluctuations. It provided the scaffolding upon which galaxies could grow. Ordinary matter followed the gravitational framework created by dark matter. Stars ignited, galaxies assembled, clusters emerged. Over billions of years, the vast cosmic web took shape. In this sense, dark matter may have served as the invisible architect of cosmic structure. The galaxies we admire today may owe their existence to something we still cannot directly observe. That thought carries a certain quiet wonder. Every spiral galaxy, every glowing nebula, every planet, every future civilization, perhaps all of them emerged within an unseen framework stretching across the cosmos. And tonight, as we drift through this mystery together, dark matter remains one of the greatest unanswered questions in science. Not because we lack evidence. The evidence is abundant. Rather, because the evidence points towards something profoundly unfamiliar, something that fills the universe, something that shapes galaxies, something that guided cosmic history from the beginning, yet something that still hides beyond our direct sight. And perhaps that is what makes the mystery so beautiful. The universe has not revealed all its secrets. Not yet. Somewhere beyond the stars, beyond the glowing galaxies and the luminous clouds of gas, an invisible reality continues to shape the cosmos. Silent, unseen, patient, waiting for future generations to uncover what it truly is. Here is the next section for Outline 15, How Will the Universe End? Written in the same calm, immersive, sleepy science style and continuing naturally from the hook. The question of how the universe will end is one of the most profound mysteries in all of science. It is a question that stretches far beyond human history, beyond civilizations, beyond planets, and even beyond stars. Every sunrise, every mountain, every ocean, every galaxy we can see today exists inside a universe that is changing. Nothing remains exactly as it is. Stars are born, stars die. Galaxies collide, space itself expands. And because the cosmos is constantly evolving, scientists naturally wonder what its final destination might be. Will the universe continue forever? Will it eventually stop? Or is there some unimaginable future waiting beyond everything we currently understand? The remarkable thing is that the answer depends on forces that are operating right now. The future of the cosmos is not determined by events that have yet to happen. It is being shaped at this very moment by the invisible properties of space itself. To understand the possible endings, we first need to remember a discovery that changed astronomy forever. In the 1920s, astronomers realized that galaxies were moving away from one another. The universe was expanding. For a time, many assumed that gravity would eventually slow that expansion. After all, gravity pulls things together. Galaxies attract galaxies. Matter attracts matter. Perhaps the expansion would gradually weaken until the universe eventually stopped growing. Perhaps it would even reverse. For decades, scientists debated this possibility. Then, near the end of the 20th century, something astonishing was discovered. The expansion of the universe was not slowing down. It was speeding up. Galaxies were drifting apart faster and faster as time passed. Something seemed to be pushing the cosmos outward. Something invisible, something powerful, something that remains largely mysterious even today. Astronomers call it dark energy. And dark energy may ultimately determine the fate of everything. The simplest possibility is sometimes called the heat death of the universe. Despite its dramatic name, this ending is not violent. It is slow, almost unimaginably slow. In this scenario, the expansion of the universe continues forever. Galaxies drift farther apart. Stars gradually exhaust their fuel. New stars become increasingly rare. Over trillions of years, the bright age of the cosmos slowly fades. Imagine looking into the night sky far in the future. The familiar constellations would be gone. Many neighboring galaxies would have disappeared beyond the observable horizon. The universe would become darker, quieter, older. Eventually, even the longest-lived stars would burn out. White dwarfs would cool. Neutron stars would fade. Black holes would slowly evaporate through a process known as Hawking radiation. Given enough time, even these mighty objects might vanish. What remains would be a vast universe filled with thinly scattered particles and faint radiation. No great explosions, no dramatic collapse, only an endless drift toward maximum entropy. A cosmos growing colder and quieter with every passing age. There is something strangely peaceful about this vision, not because it is comforting, but because it unfolds with extraordinary patience. The universe would not die in a single moment. It would simply grow older until almost nothing remained capable of change. Yet heat death is not the only possibility. Another scenario is far more dramatic. It is known as the Big Crunch. In this model, expansion eventually stops. Gravity gains the upper hand. Galaxies begin moving toward one another instead of away. Space itself starts shrinking. Over immense spans of time, the entire universe collapses inward. The process would resemble a reverse version of cosmic history. Distances would decrease, temperatures would rise, matter would become increasingly compressed. The cosmos would grow denser and denser. Eventually, everything could converge into an extraordinarily compact state. A final collapse, a cosmic ending that mirrors the beginning. Although current observations suggest this outcome is unlikely, it remains one of the most fascinating ideas ever proposed. There is something deeply symmetrical about it, a universe that expands from a tiny beginning only to return to one. A cosmic breath, an exhale followed by an inhale. Some scientists have even imagined that such a collapse might trigger another Big Bang. Perhaps the universe could be reborn. Perhaps endings and beginnings are connected. Perhaps the cosmos operates in cycles far larger than we can comprehend. Then there is an even stranger possibility, a future known as the Big Rip. This scenario depends on dark energy becoming increasingly powerful over time. If that happens, expansion would not merely continue. It would accelerate relentlessly. At first, galaxies would be pulled apart, then galaxy clusters. Eventually, entire galaxies themselves would lose their structure. Stars that once orbited peacefully around galactic centers would drift away. The expansion would become so strong that solar systems could no longer remain bound. Planets would separate from their stars, moons from their planets. In the final stages, the process becomes almost unimaginable. The very fabric of matter could be torn apart. Atoms, molecules, even subatomic particles, everything would be overwhelmed by expansion. Space itself would become the ultimate force of destruction. The universe would not freeze, it would be ripped apart. Fortunately, current observations do not strongly support this scenario, but the fact that it remains mathematically possible reminds us how little we still know about dark energy. And that uncertainty is perhaps the most fascinating part of all, because despite all our telescopes, satellites, and calculations, we still do not fully understand what drives most of the cosmos. The future remains partly hidden. The universe continues to keep some of its deepest secrets. Perhaps that is fitting. After all, every generation has looked upward and wondered what lies beyond the horizon of knowledge. The ultimate fate of the cosmos may simply be the largest horizon of all. Tonight, as you rest beneath the stars, it is worth remembering that these endings exist on timescales so vast they almost lose meaning. Trillions, quadrillions, numbers so enormous that human history occupies only the tiniest fraction of a moment. The stars above you will shine for ages yet. Galaxies will continue their slow dances. The cosmos remains young compared to the futures being imagined. And somewhere within that immense unfolding story, our small world continues to circle an ordinary star in an ordinary galaxy, quietly witnessing a universe whose final chapter has not yet been written. The ending remains unknown, and perhaps that mystery is one of the most beautiful things about the cosmos. After all the equations, telescopes, and discoveries, one question remains, a question so simple that a child can ask it, and yet so profound that some of the greatest minds in history have spent their lives trying to answer it. Why does anything exist at all? Why is there a universe instead of nothing? Not merely why stars exist, not why galaxies formed, not why planets orbit suns, but why there is anything to begin with, why there is matter, why there is space, why there is time. Why there is a reality capable of producing observers who can ask these questions. As our journey through cosmic mysteries draws toward its final destination, we arrive at a puzzle that sits beneath all the others. Dark matter may remain unseen. Dark energy may remain unexplained. The origins of the Big Bang may still be uncertain. But all of those mysteries already assume that something exists. This final question asks why existence itself is here at all. And strangely enough, the deeper science advances, the more fascinating that question becomes. For most of human history, people simply accepted existence as a given. The sky was there, the earth was there, the stars were there. Reality existed because reality existed. Yet modern physics has revealed that many aspects of our universe seem extraordinarily delicate. Tiny changes in certain physical constants might have produced a cosmos completely different from our own. A universe where stars never formed. A universe where atoms could not exist. A universe where complexity never emerged. Or perhaps no universe at all. The strength of gravity, the mass of fundamental particles, the properties of electromagnetic forces. Many of these values appear to occupy remarkably narrow ranges. Change them only slightly, and the universe might become sterile and empty. This observation has led to one of the most intriguing discussions in modern science. Why do these numbers have the values they do? Were they inevitable? Were they random? Or is there some deeper explanation waiting to be discovered? The question is often called the problem of fine-tuning, and although it remains controversial, it highlights something remarkable. The universe we inhabit appears capable of producing galaxies, stars, planets, chemistry, and eventually life. That fact alone can feel astonishing, because the cosmos could have been very different. Imagine a universe where gravity was just a little weaker. Matter might never gather into stars, no stellar furnaces, no heavy elements, no planets, no oceans, no life. Or imagine gravity slightly stronger. Stars might burn through their fuel far too quickly. The long, stable periods needed for biological evolution might never occur. Again, no observers, no questions, no stories, no wonder. The existence of complexity depends upon a surprisingly delicate balance. Yet perhaps the greatest surprise comes from quantum physics. For centuries, people assumed that empty space was truly empty, a perfect void, absolute nothingness. But modern physics paints a stranger picture. Even what we call empty space is not truly empty. Quantum fields permeate the universe. Tiny fluctuations constantly appear and disappear. Particles briefly emerge before vanishing again. The vacuum itself possesses structure, energy, activity. In some sense, even nothing appears to be something. This realization creates a fascinating challenge. When people ask why something exists rather than nothing, what exactly do they mean by nothing? A universe without stars? Without matter? Without space? Without time? Without physical laws? The deeper we examine the concept of nothingness, the more elusive it becomes. Perhaps true nothingness is far harder to define than existence itself. Some physicists have proposed that universes may naturally emerge from quantum processes. In certain models, entire cosmic regions could arise from fluctuations within a larger framework. Space itself might generate new space. Universes might appear like bubbles forming within an enormous cosmic ocean. Such ideas remain speculative, yet they reveal how modern science increasingly explores questions once considered purely philosophical. The boundary between physics and philosophy becomes blurred. And perhaps nowhere is that boundary more fascinating than here, because eventually every explanation seems to lead to another question. Why do quantum laws exist? Why do physical laws exist at all? Why is mathematics so effective at describing reality? Why should the universe follow understandable rules? Each answer appears to open another door, another hallway, another mystery waiting beyond. In that sense, the search for ultimate explanations resembles standing before an endless horizon. No matter how far we travel, there is always another distance beyond. And perhaps that is not a failure of science. Perhaps it is one of its greatest strengths. Science does not promise final certainty. It invites continual exploration. Every generation inherits unanswered questions and contributes new understanding, then passes those mysteries forward. The universe remains larger than any explanation we currently possess. That realization can feel humbling, but it can also feel beautiful, because mystery is not the opposite of knowledge. Mystery is what makes knowledge worth pursuing. Without unanswered questions, discovery would end. Without uncertainty, curiosity would fade. Without mystery, there would be no journey. And what a journey it has been. Tonight we have wandered across immense distances. We have traveled through dark matter halos and invisible cosmic webs. We have drifted among rogue planets, wandering through endless night. We have explored black holes, ancient stars, mysterious radio signals, hidden forces, and the possible futures of the cosmos itself. Yet after all that travel, we arrive at a question even larger than the universe. Why is there something rather than nothing? Perhaps one day humanity will discover an answer. Perhaps future generations will uncover laws of nature that make existence seem inevitable. Or perhaps the mystery will remain, a permanent companion to conscious beings looking up at the night sky. There is something strangely comforting about that possibility. Not every mystery must be solved immediately. Some questions can simply accompany us, like distant stars on a quiet evening, like waves on a dark shore, like the gentle movement of galaxies across cosmic time. The universe does not owe us complete understanding, and yet it has already revealed extraordinary wonders. Enough wonders to fill countless lifetimes. Enough wonders to inspire countless dreams. Enough wonders to remind us that existence itself is an astonishing thing. Right now, as you rest beneath the same cosmos that inspired generations before us, countless stars continue shining across unimaginable distances. Galaxies continue drifting through the darkness. Planets continue orbiting silent suns. And somewhere, perhaps far beyond anything we can currently observe, new mysteries are waiting. Perhaps that is the final lesson hidden within all these cosmic questions. Not that we must know everything, but that wonder itself is valuable, that curiosity is worthwhile, and that the universe remains vast enough to surprise us forever. Thank you for joining this peaceful voyage through some of the universe's deepest mysteries. As the stars drift quietly across the darkness, allow your thoughts to grow lighter, your breathing slower, and your mind calmer. The galaxies can fade now into the distance. The questions can rest for a while. The vast universe will still be there tomorrow, carrying its secrets through the endless night. Sleep peacefully tonight, knowing that the cosmos still holds wonders waiting to be discovered. Good night.